Hello and welcome everyone. My name is Dane Menke. I am the Digital Marketing Manager here at Regenesis and Land Science. Before we get started with the webinar today, I have just a couple of administrative items to cover. Since we're trying to keep this under an hour, today's presentation will be conducted with the audience audio settings on mute. This will minimize unwanted background noise from the large number of participants joining us today. If you have a question, we encourage you to ask it using the question feature located on the webinar panel. We'll collect your questions and do our best to answer them at the end of the presentation. If we do not address your question, we'll make an effort to follow up with you after the webinar. We are recording this webinar, and a link to the recording will be emailed to you once it is available. In order to continue to sponsor events that are of value and worthy of your time, we will be sending out a brief survey following the webinar to get your feedback. Today's webinar will focus on overcoming vapor intrusion mitigation, design, and constructability challenges at 2 large industrial sites using an innovative new vapor barrier technology. With that, I'd like to introduce our presenters for today. We are pleased to have with us Mark Quimby, Senior Consultant at SME. While at SME, Mark has established himself as a top expert in the field of assessing and mitigating petroleum, chlorinated solvent, and methane vapor intrusion sites. During this time, he has designed and installed dozens of vapor intrusion mitigation approaches, including subslab passive venting, multiple types of vapor barriers, active subslab depressurization, and passive interceptor trenches. We're also pleased to have with us today Ryan Miller, East Region Manager for Land Science. Ryan's role includes providing technical support in the design and installation of vapor mitigation systems for new building construction and existing structures, as well as informing the environmental community of recent advancements in vapor intrusion barrier technology, implementation, and quality control. Ryan has extensive experience in the environmental consulting industry, which focused on brownfield redevelopment projects. All right, that concludes our introduction. So now I will hand things over to Mark Quimby to get us started.
Thank you, Dane, and thank you everyone for joining us. I'm excited here to talk about the VI mitigation design and constructability challenges and using an innovative new vapor barrier technology. I'm going to get right into it. A brief overview of the talk today. We're going to have an introduction about my company and myself. Then we'll get into the projects that we're going to be talking about that primarily deal with the vapor intrusion aspects of those projects. We will discuss the vapor barrier selection that we went through and where we ended up. We will talk about our vapor intrusion system design and approval. And then we'll talk about the actual construction of the system and some conclusions and lessons learned. And I know there will be questions, time for questions at the end. So getting right into it. So who is SME? We are a multi-service engineering and consulting firm. We've been around for about 65 years, and primarily SME was started by a geotechnical engineer and over time grew in both service offerings and clients built around that basic kind of initial history. So one of the things when we deal with projects is, looking at the full range of life cycle from acquisition through design, construction, and restoration. But we have a very strong construction focus. I'm in the environmental group, and we obviously deal with a lot of remediation. We deal with some big liable party cleanups, but I would say the bulk of our work is in brownfield redevelopment, focusing on developer clients. Our offices are in Michigan, Indiana, and Ohio, and we recently opened one in Louisville, Kentucky on the southern tip of Indiana. Historically speaking, we grew out of Michigan, and that's where I would say the majority of our business is, but we've been established in Indiana and Ohio for quite a few years now. A little bit about myself. I spend the majority of my time practicing at the intersection of construction on environmental contaminated sites in the Metro Detroit area. I work in all 3 of our states. I work all over the state of Michigan, but the bulk, I would say, concentration of my practice is in the Metro Detroit area. And I'm going to explain why vapor intrusion is so important to my projects. So most of the sites in the Metro Detroit area are supplied drinking water by the municipal water system, primarily coming from the Detroit River, and then in some of the metro communities, as you get maybe outside of the metro area, but still within that kind of southeast portion of Michigan, some people are getting their water from Lake Huron or maybe even Lake St. Clair. But because of that, the drinking water pathways, honestly, it's not that commonly complete. Drinking water cleanups do happen, and as you get outside of metro areas, people for sure are on wells. But when you look at the bulk of industrial sites that I'm mostly focusing on redeveloping, those sites are typically pretty close to the Metro Detroit area and are serviced with drinking water. So it's not a big concern. Contact with contaminated soil is also generally, it's essentially on every single site. But the thing is most of these sites I'm working on have very large buildings with big parking areas and trailer truck staging. So the majority of the site is covered by building or pavement with some limited landscaping. And that limited landscaping, can be large, but from a mitigation perspective, a landscaping fabric as an exposure barrier with some soil on top goes a long way. And I would say that, it's a real cost, it happens, but it doesn't drive the environmental risk typically for the final use of the site, because the standard construction we're already going to do is going to address that. Now, there are a lot of details that we often get involved with on a soil management side of things, where there's a tremendous amount of money to be saved or lost if it's done improperly, but that's not the focus of this talk. So vapor intrusion is by far the environmental risk driver for my projects. And the reason why is pretty simple. Everybody has to breathe. The indoor air inhalation pathway is always relevant. And another big thing that we've seen over the last decade or so as VI has become a larger and larger issue is that, when you have a vapor source present, the off-ramp to document that mitigation is not necessary is not simple. It typically requires a lot of characterization, and often you might be in a position where the amount of characterization that you feel is adequate does not meet what the regulator thinks is adequate. So you have to go back and do more. They typically require multiple sampling events to account for seasonal variation, which is a documented effect. And then also, these two things combine to create a lack of timely certainty in decisions. Because the thing is that a lot of these brownfield sites that I work on, the state is involved in some way or another, whether it's on a strict, maybe it's on a liable party side if it's being redeveloped, or it's on a, they're getting involved with some kind of incentive. And so their hand is in the cookie jar. And the thing is that if I have to wait a year to get seasonal data to know if I even need a vapor barrier, then I still got to submit a vapor barrier for them to approve. And that process could take 3 to 6 to 9 months. That just doesn't work with the development time frame. So these factors work together to push most of my projects to VI mitigation. And some sites that are low risk, they get pushed into it for the factors above. Some sites that are, a bigger risk, like the sites I'm going to be talking about today, there's not really any question. They need to be mitigated. So those are the reasons why VI is generally driving a lot of kind of the environmental risk side of my projects. And so here we're going to talk about, for the rest of the talk, 2 projects which were kind of managed as one big project. And a big client of mine, my best client, Ashley Capital, they're an industrial developer client. They were going to build 2 large logistical warehouse buildings about the same time, approximately 7 miles from each other in Metro Detroit. And that picture is kind of it's actually one of the buildings, and it's what their typical buildings look like. This is a kind of a picture of Metro Detroit. I think you can see my mouse. One site here is in Hazel Park, and you can see that it's right at the intersection of Interstate 75 and Interstate 696. That's a very typical building location that Ashley Capital likes to build on. It's very close for the logistical hubs. The other site is up here in Sterling Heights, and it is further from freeways than would typically be chosen by them. But the road that it adjoins, that it's on here, Mound Road, is a major industrial corridor in the city of Sterling Heights. And this entire area is just full of tier 1, 2, and 3 suppliers. And there's actually a stamping plant just to the north of the site. So it was a good ideal location for them to put a logistical warehouse building. So for context, the first building is about 575,000 square feet, and the second building is approximately 650,000 square feet. It's interesting because they're completely separated by location, but both sites happen to be on unlicensed landfills. Not so much municipal solid waste, there wasn't any evidence of that, but they were filled with incinerator waste. And I'll talk a little bit about those sites in a second. The subsurface methane levels exceeded the LEL by quite a bit, and in many locations exceeded the upper explosive limit as well. So there's no question that methane was going to have to be dealt with. And building 2 also had an area with some low-level TCE that was relatively isolated. And so, as I mentioned, a VI solution was going to be needed for these buildings. This is building 1, the one in Sterling Heights. You can see Mound Road right here. It used to be a park, Liberty Park. It was used as an uncontrolled, unlicensed landfill in the 50s and 60s, roughly. Low-lying areas around this creek were filled in to make flat space. It was vacant for a while, and it was developed with a ballpark that had a thin cap on it. And when we did our investigations, we found that there was methane levels far in excess of the explosive limit and even the upper explosive limit, so definitely needed to be addressed. The second building in Hazel Park was on the former Hazel Park Raceway. If anyone is familiar with the Metro Detroit area and that raceway, I actually went there once when I was younger and bet on some horses. It was fun. But the raceway did not make it, and it was bought by Ashley Capital. It's a 160-acre parcel. They actually developed the first phase, which was over kind of a vacant parking lot portion of the parcel in about 2016. We worked on that. And then this part, they were focusing on building 2, but then after building 2, they were also going to build building 3. Apparently this site was mined for sand, which we believe was part of the build up to World War II. It happened really fast, as you can see it on aerials. We believe that they probably used the sand to make concrete, maybe with the Willow Run bomber plant, which is kind of an interesting arsenal of democracy history buff kind of thing. But the site was filled with all of this incinerator waste, and we had some TCE in a limited area, and then we had methane kind of throughout the site. The source of the TCE was unknown. We don't really know where it came from. It was kind of near some horse barns, so we believe it was not like some kind of big source of point source release, but it was likely maybe some maintenance of some kind that somebody did in that area. So, construction issues for these 2 sites. An important note is both buildings were speculative, which means they had no tenants when they started to build it. Ashley Capital has made a tremendous business model out of this. They have some very good, smart people making good decisions about where the market is going, and they build buildings, and when people need buildings, their buildings are ready, and they typically have these leased before they're even built, but they often start them without having anything. But because of that, they needed the building to be flexible so that they could modify it as necessary to the floor and interior utilities, which becomes a problem because most vapor barriers are typically placed directly beneath the floor, which means every time you touch the floor, you'd have to do something to the vapor barrier, and that's problematic. From a scheduling perspective, building 1 was slightly ahead of building 2, and the client wanted the vapor barriers to be installed concurrently as the earthwork contractor prepared the subgrade for both sites. So that was something we had to take into account in terms of kind of the scaling up. So we weren't really doing 2 different buildings that was 500 or 600,000 square feet. We're really almost doing like 2 buildings, or 1 big building that's 1 million square feet that's separated by 7 miles. So that was a logistical challenge we had to overcome. Another thing that the client did not want to pump concrete. So if you have the vapor barrier directly beneath the slab, then to get the concrete slab on top of the vapor barrier, you have to put the concrete there. And typically on most sites, if the vapor barrier is directly beneath the concrete, you achieve that by building it in sequence phases. And when the building's not that big, it's not that big of a deal because the boom of the concrete truck can reach far enough. But for a huge site like this, that's not really feasible. So typically what you would do is you would pump concrete so you could pump it over long distances, but that had costs associated with it, it had time associated with it, and the client didn't want to deal with that. So they commissioned us to figure out a way to solve that problem. Oops. So into the vapor barrier selection. So for typical selection, when you're looking at what vapor barrier is going to solve your problems, you're going to look at chemical resistance, you're going to look at physical durability. This was a big one for us. You're going to look at ease of installation, because that often translates almost directly into dollars in terms of how cumbersome it is and labor intensive it is to install. You're going to look at ease of repair if there's a problem in a particular, as I'm going to talk about in a second, with smoke tests. And you're going to look at what the cost is and what the price point is. So that being said, I've got a slight sidebar that is directly related to the vapor barrier kind of selection process, which is smoke tests. Now, typically when you're looking at vapor barriers, there's spray applied barriers, there's taped rollout seam barriers, there's welded seam barriers, there's a lot of different kinds. Not all these barriers have in their manufacturer specs that require smoke tests. Most of the rollout barriers that I've seen that have taped seams do not. In my experience, I don't recommend installing any vapor barrier without smoke testing it. I mean, the whole point of a vapor barrier is to prevent VI through the membrane, and I think that you should verify that you don't have leaks that would just bypass the barrier so that you paid for and installed. That's not to say that the barriers that don't require smoke tests as part of their specifications are not good. I just think, you know, you should do that as an add-on and smoke test it. So I'm going to go over kind of our thought process as we looked at the different choices that we had to make in terms of what barriers were available. And one of the points I want to make is I'm not endorsing or devaluing any product or method. I want you to know that every project is its own animal, and you can often use examples from one and apply them to another with, you know, experience, but it's a site-specific thing, and we just want people to make sure that, you know, you do your due diligence on what you need for your site. So we looked at 3 different types of vapor barriers. They each had similar price points and adequate chemical resistance for methane and the TCE concentrations we were managing. So I'm not going to talk a lot about the price and the chemical resistance because all 3, I mean, they weren't all the same, but they all met kind of the minimum standards that we were looking for. And from a price point perspective, I believe Ryan's going to talk more about it for Monoshield in particular. But for us, we wanted something, we knew that it was going to be probably north of $1 a square foot, but we really wanted to be south of $2 a square foot, and the closer to 1, the better. Also, because this is a methane system, we went with a passive system. I typically use a lot of active systems for more significant TCE releases, but for some like petroleum sites, in particular for methane sites, I generally prefer to do passive systems. So, looking at the different products that we looked at, the first one we looked at was a Raven Industries Vapor Block 20. It's a good product. We've used it on many sites. It's a sheet product, so it rolls out in big rolls, and then you tape the seams together. And it has like a 2-sided tape, a butyl seam tape, and also a 1-sided tape that they use. They have penetration details, wall termination details. They have all the details you would want. The pros for this is that it's got acceptable durability compared to other things for a similar price point. It's easy to install and roll out. There's a caveat though. And the caveat is that in my experience, in particular with inexperienced contractors, they don't, when you're going to tape something together and that's the seal, you really have to have it flat. It has to be flat, it has to be flush against the walls. And I have found that these systems often fail smoke tests if not installed by someone who really knows what they're doing because they don't pay careful attention to things like that. That being said, it's easy to repair. It doesn't need special equipment. Everything you can kind of just buy. The tape comes in rolls, and it's efficient to put over large areas. The con, as I kind of alluded to, is I have found that in particular, it can be challenging sometimes with smoke tests for this system and to get the seams to lay completely flat. And you know, we're going to talk about spray applied barriers in a second, but one of the things that for me that really stands out with some of the tape systems that's problematic is that, and again, I don't mean to say they don't have their uses, I use them all the time, but for certain projects, it's that when you have a failure of a smoke test, how do you fix it? And with a spray applied system, you can fix it by spraying more and basically just building more barrier up and covering and sealing it. But with a tape system, you know, a lot of times you can't fix it by something easy. You have to basically pull it apart and put it back together again. And if you have lots of failures, all of a sudden something that was really easy and efficient to install ends up becoming a lot harder and more expensive because you have to keep going back to the weld. And especially on like wall terminations and things like that. So the second system we looked at was a full spray applied barrier. And since this is a land science webinar, I'm sure most of you are familiar with the Geoseal system. What we used or looked at as a candidate for this was what we call a modified Geoseal system. We've used it on some sites. And we actually use this on the first building that we did in the Hazel Park Industrial Park. And what it is, instead of using the typical bond and base layers with Geoseal, it's a 5 mil plastic sheet, only a 30 instead of a 60 spray applied layer, and then a 5 mil sheet on top. This is not appropriate for all sites. It is a good solution for some very low level sites, in particular methane sites. There's some cost savings on the sheets and the 30 mil that allow it to be a lot more cost competitive than, say, something like a full Geoseal system. But if you have significant chemicals, this would not be an appropriate chemical or resistant system to use, and you would want to go with the full Geoseal. So some pros, similar, the durability is acceptable, but it needs some modifications because the 5 mil plastic sheets can rip. So if we were going to go with this system, we would have to potentially protect it with some GeoTextile fabrics. And we have to take that into account in terms of the labor cost and whatnot. When we did that actually on the first building. It is excellent for smoke tests because you're essentially building the barrier as you go in place. And so when you're doing a smoke test and you have a failure, it is very easy to fix that failure and move on. So that's good and easy to repair. And that's kind of what I was referring to. The cons of this is that there's a lot of labor time to spray apply the barrier over a large area. You need a specialty contractor with special equipment for installation. Just not anyone can install something like this. With that caveat being said, although someone could buy a tape system off the shelf and theoretically install it, I don't recommend people who aren't familiar with it and don't know what they're doing install these systems, because if you do smoke test them, as I recommend, they will likely fail. And they will likely need to have significant repairs done to them to get them to pass a smoke test if they're not installed by a quality contractor. And because you need a specialty contractor, you're going to have a smaller pool of people available, and they'll often need to remobilize, sometimes from distance, to fix something if something needs to be fixed later on. And finally, we looked at this new innovative product, Monoshield, which you probably guessed by now, this is the one we picked. It is a sheet product, but it uses spray applied seams. So it doesn't use two-sided or single-sided tape at all. It is 100% rollout and spray seams. And its pros, it's got really nice durability. In particular, over the spray applied modified Geoseal system, we weren't going to need to use a GeoTextile, at least on the bottom. Excellent for smoke tests, easy to tell if you have a hole and easy to fix, easy to repair. The asterisk is coming, just the idea that you need a specialty contractor to do it. And they are very efficient over large areas. The con, again, is you need a specialty contractor with special equipment for installation. For small fixes, often the contractor or land science can send you a bucket of their kind of spray applied component in a kind of paint grade. But that is for very small fixes, and anything significant, you need to remobilize the contractor. So we selected Monoshield, and the reason why is we believed it combined the advantages of both the sheet product system and the spray applied system. And what's interesting about these projects, is that I had been complaining to land science for some time about, I was hoping that they would have a product that would essentially compete at a price point and a practical of installation perspective to something like a vapor block. I think they have a great team and I liked working with them, but sometimes they just, the Geoseal system was too expensive and it didn't work for me. And I really wanted spray applied seams though. And I've heard of some people using something like a vapor block and then using, maybe like an off spec, like a liquid boot or something like that to seal the seams, and that might work, but you have two different companies and typically they won't respect the warranties because you're not using it as designed. So I really wanted to use something like Monoshield, and I was very excited when they told me about it. And the timing of the projects worked out that we actually didn't think we were going to be able to use Monoshield because it just wasn't market ready when we needed it. And we almost didn't use it, but then they came through at the last minute and they were able to meet the project needs and production capacities and commitments that we needed. And so we were, I believe, the first site to use this, and it was a big sites at that. So that's the way we went. So VI system design and approval. So now we picked Monoshield, but we still had these lingering client needs that we had to resolve, which was we had to drive concrete trucks on it. And we wanted flexibility for future slab and tenant modifications that hopefully wouldn't require the contractor that would install Monoshield to constantly remobilize every time they needed to change something. So we worked with our geotechnical group, the construction team, both internal and also the development team with Ashley and their contractor, Oliver Hatcher, and the line science team, who have been kind of a partner of ours as well and worked with us. And we developed a workable plan that would achieve both of these goals while protecting the barrier system. And so before I get into that, just some brief context. This is what the system looked like. The two buildings were almost the same, just slightly different in size. So they pretty much looked the same. They had a bunch of loops of low profile venting from the Land Sciences vapor vent. And we connected them all to 4-inch vent risers with loops. And then there was 1-inch test ports spread throughout the floor. A lot of times people will use like vapor pins to collect readings beneath the floor. But in our case, the client did not want us having to like get on the floor all the time. So we basically made stick up pressure ports. So building 1, which was 575,000 square feet, had 26 4-inch vent risers. And this is kind of a side thing, but we ended up, putting wind turbines, which is typical for passive systems. But for 8 of the 26, we actually put these things called aerofoils, which is the picture here, just underneath the typical fan. And what it is it's a cap that basically has an aerodynamic structure that disrupts the airflow across it and creates a suction that's similar to a fan. And what we wanted to do was kind of use this as a test case and check its performance against the traditional fan, because it doesn't have any moving parts. And so there's some advantages in terms of maintenance. And Ashley Capital was on board with us trying that, because we end up working on a ton of their sites, and they were willing that if it didn't work, we would just replace those 8 with traditional fans, and it wasn't going to be a tremendous cost. And then, as I mentioned, we had several 1-inch test ports. Building 2 was 650,000 square feet, almost the exact same. It was about a bay bigger on one dimension, and I believe one more on another dimension. And we had 33 4-inch vent risers. Again, we had 8 of them kind of strategically placed and capped with aerofoils. And as I mentioned, we installed the aerofoils because we wanted to just see how they were going to perform, because you can read the spec books, but the proof is in the pudding when you actually build it. So what did our vapor system profile look like? From top to bottom, we had subgrade. Then we put on 6 inches of 21AA crushed stone. 21AA is a Michigan DOT spec, but all DOTs have a similar type of spec. It's basically an interlocking mix that has fines in it, so that it basically locks together very tight. All the pieces jostle together under compaction, and it can form a really good bridge, both for to withstand structural forces, but then also it can choke off. It's often used to choke off, like if you have groundwater, you can have crushed 1x3 that you dump into the groundwater, get above that, and then cap it so that you don't lose any fines, don't come down and choke out the layer. In our case, what we wanted to do was we put 4 inches of 6AA, which again is an MDOT spec. Every state has something similar, but this is a crushed stone that doesn't have any fines in it. And the purpose of the 21AA below it was to stop us from, any subgrade fines migrating upwards into the crushed stone. We could have also done like a GeoTextile barrier underneath this to do the same purpose, but the client was building the building up anyway, so they wanted to use stone. Inside of this 6AA, we had Land Sciences vapor vent, which is a 12-inch wide, 1-inch high profile that has a similar cross-sectional flow to a 3-inch PVC pipe, slotted pipe. We use that pretty much on all our sites. Then we put down the Monoshield vapor barrier, but then on top of the Monoshield vapor barrier, we put a Merafi 600X GeoTextile, which is essentially a road construction fabric. It's often used over bridging poorly performing soils where you don't want to do significant undercuts, like kind of a marshy area. But the purpose of it is to basically distribute forces above it over a larger area, so that you have better performance and less kind of force shocking the underneath it. On top of this, now we have 8 inches of 21AA crushed stone again, with the interlocking mix. And what this is functioning is it's actually serving 2 purposes. It's actually going to protect the Monoshield system that's buried under the GeoTextile from the construction traffic, And it's also going to give us 8 inches of buffer to mess around with utilities if we need to with the tenant. And then on top of that, we have a 7-inch concrete slab. And so, as I mentioned, we worked with our internal team and also the land science people and the construction team, and looked at, what we expect the shear strengths to be. I mean, it's simple to show it as a picture, but there was a lot of thought that went into this in terms of, would it hold up? This is what we went with. A couple comments here about VI design. I mean, it's really important that it doesn't start or end, let's say, with picking a barrier and then just slapping it together. And as I said, if you do that, you're generally going to run into big problems. You want a qualified contractor who knows what they're doing, has done this before, and in particular has experience with smoke tests, because if they don't do smoke tests, I question how they have experience building barriers that are actually gas tight. Always take into account the building specific needs. And remember that the membrane is designed to prevent barriers from diffusing across them. But if vapors can go around them because you have leaks, then they can't function as they're designed. So what did we do? So we have that profile, right? But we have to protect it. So we worked with the construction team. We developed an installation and sequencing plan. We worked with install crews that would follow behind the earthwork people as it was placed. The VI team would basically complete Monoshield over a completed subgrade area with the venting layer at building 1. Then they would move to building 2, which was just getting ready for them. While they were gone, the contractor was taking another giant section of the building and preparing it for more vapor barrier installation. And then the crew would flip-flop between the buildings, simultaneously working with both as they were installed. We also developed a construction traffic control plan to minimize stress on the vapor barrier for the stone placement. No tight turns were allowed on any finished portion of the barrier. Trucks were limited to slow speeds, and we used a very careful dump and push method to place the stone above the barrier. And the bulldozers had to minimize their turns and be slowly and carefully. And all of this was monitored so that if someone got crazy or made a mistake or just forgot what they were doing, we would then know to go and re-inspect that barrier and make sure that it was still okay. Our smoke testing program also had 2 components. We had the typical smoke testing, which I'm not going to talk about a lot, but it's your typical smoke testing that you would do for a vapor barrier. But then we also had secondary smoke tests, so that after the barrier was placed and then the GeoTextile was placed, then the stone went on top. And once the stone was placed and compacted, we then did another smoke test using the networks of test ports and vents that were basically stubbed up to push smoke beneath the barrier and essentially do a check to see if there was any leaks. And you would wonder if that would work, and I'll get into it. And this actually methodology did work quite well. So the system design and package was submitted to Michigan's Department of Environmental, Great Lakes, and Energy for review and approval. We worked through 2 rounds of comments with them, and then received approval to proceed with construction, including, the profile, the traffic control plan. All of those pieces were in our state approval. And we needed the approval because although we were not dealing with a liable party, and in the state of Michigan, the laws are such that, you can achieve protection from cleanup responsibility for pre-existing condition. You still have due care, you still got to use it safely, but you don't have to necessarily chase cleanup. But we still needed the state's approval because they were helping fund some of the project with incremental taxes, as what happens with most of my brownfield projects. And this is often necessary because, frankly, without it, the negative equity created from the brownfield conditions would just drive everyone to build on farm fields, which is a whole land use issue on why brownfields are so important. So now I'm going to get into a little bit more detail with the little bit of time we have left on the actual construction. This is an example of the sequencing plan that we used. The numbers are basically the order in which areas were done, and the colors are groups of areas that were done at once. So if, for instance, on this particular building, area 1 and 2 were done together, and then they basically finished those areas and then demobbed, went to the other building. And then the contractor, while they were doing that, the contractor was working on 3, 4, 5, and 6 to prepare subgrade and get the 6AA where it needed to be. They would then do kind of a similar area at the other building. They would come back and do 3, 4, 5, 6. While they were doing 3, 4, 5, 6, the contractor then started on 7, 9, and 10. and then the arrows are roughly the direction of traffic flow. And then here's some pictures, kind of just showing the installation process. You can see the building shell was up when we were doing the work. We had a roof, we had walls, but not doors. And where there was lots of truck docks, we did have some issues with wind. You can see they're putting down some vapor vent here, but this picture is nice because it shows some of the efficiencies that you can get with a rollout system. Because you can see they roll out these sheets and just, they can do several of them at a time and then go and seal all the seams kind of in one swoop. And so we were able to really get some nice production capacity. Here's another example. You can see they're still installing the system. You can see the building and kind of what's up and what's not. But they would essentially do, mass rollouts of sheets. Well, I guess I would back up. First, they would put in the vapor vent, right? They would do that first. Then they would put mass sheet rolls down once it was ready to go, then seal all the seams, and then put the GeoTextile on top. And you can see here they're working through, they're sealing seams, and they were able to do pretty large areas in one fell swoop. Because of the efficiency of the Monoshield system and just the way that it was put down, it was really, I was very impressed. It was very nice. In particular, being able to do such large areas in big chunks. And because we weren't tied to the pour schedule, which was often a driving force with a lot of projects, we were able to do huge sections at a time. Here you can see just them pushing some stone around. Kind of you can see what the building looks like here as they prep it. Again, this is just sort of what it looks like as they're putting down the Monoshield, and you can see a lot of seams are already done. This has already been smoke tested. Here again, you're seeing them spray some seams. And then here's a nice picture because you can see they're putting down the GeoTextile. This black fabric is the GeoTextile that goes on top of the vapor barrier. And then to deal with wind issues, they were duct taping these together to basically try to hold it down, because if you got a bad gust and you didn't, we'd have issues where the barrier would get lifted up, or the GeoTextile rather would get lifted up. But the barrier, since it was spray sealed together and tied into the columns, didn't move. Here's a picture that kind of shows the dump and push that was going on. So here you can see the GeoTextile, the black fabric is down. The Monoshield system is actually installed and beneath it. And now they're taking the bulldozer and they're pushing the stone out. And again, like very carefully. So a lot of times what they would have is like a ramp at the edge of the system that they then have to dig out again later. And they would then, they would do their turns with the bulldozer kind of like off the Monoshield and then come and push it in straight rounds. And it was, they had to be careful, but it worked really well. Here's a truck driving, and it's hard to see because it all sort of looks the same, but what this truck actually is driving on right now is the compacted 21AA that has the GeoTextile and the vapor barrier beneath it. So this truck is driving right on top of our vapor barrier system. And so here we go into conclusions and lessons learned. So we were able to install the system at both sites successfully. Production was really good with the Monoshield system. They were averaging about 20,000 square feet per day across the two buildings. Building 1 was finished in about 27 days, and building 2 was about 32. Now, it wasn't 27 concurrent days because they were flip-flopping between the two, but roughly if you add the two together, that's what it took us to do the whole thing. Monoshield was about 50% faster than the modified Geoseal system that we used at the first Hazel Park building. And so I was very impressed with the amount of production that they could get down with this system, especially being the first time that it was really put down. At both sites, we had one secondary smoke test that failed. And when we looked into it, we found that the barrier was ripped from a bulldozer turning in place too quickly. And we felt really good about it. In fact, I'm kind of glad that at least one failed, so that we could go, and lo and behold, there definitely was damage, and we were able to figure out why it happened. And with the protocols in place, we felt really good about it. The system was installed on time, both projects on schedule, and as tenants were signed on, most did require barrier, or did not require barrier repairs, because the minor utility changes they had to make were above the barrier in that 8 inches of 21AA. So that saved lots of money in terms of time on remobilizations. Now, some things did go deep if they had to tap into sanitary, but in general, we were able to do a lot of work in that 8 inches. We also found similar pressure from the aerofoils than the traditional wind turbines, which I thought was really interesting, and I'm definitely going to kind of consider that going forward. And in summary, I think VI in large square foot buildings can be successfully and cost effectively mitigated when they are integrated with the construction process and not treated as a separate and unrelated issue. I think it's really important not to look at the contamination situation as some kind of different phenomenon that's separate from the construction of the building. They really should be integrated and thinking as one project. So with that, thank you. And I turn to Ryan, I believe.
Okay, go ahead.
Thanks, Mark. Really great information there. I'll be continuing the discussion on some of the same topics Mark just discussed, specifically construction considerations for vapor barrier installations. As a way of a brief background, there we go. Land Science is a recognized industry leader in vapor intrusion mitigation. We have a team position across the U.S. to provide local support to engineering firms, regulators, property owners, to ensure we're offering the safest, most technically sound, most cost-effective solutions. In addition, we're constantly working with our team of certified applicators to ensure every vapor barrier application is the highest quality installation. So our entire focus here at Land Science is to build and implement the absolute best vapor barrier solutions in the environmental marketplace. And to do that, we offer a full suite of VI technologies to ensure the right solution is selected for the right project. We can provide design assistance on any project, along with a certified installation, proper QA/QC procedures, all of which I'll discuss in a little bit more detail in the coming slides. So let's dive in. I'll focus specifically on Monoshield, Land Science's reinforced aluminum vapor barrier, just as Mark kind of touched on. Before I do that, I'd like to discuss kind of the evaluation criteria of vapor barriers in general. I know Mark just mentioned a couple, but contaminant vapor barriers are often evaluated on two primary criteria. Chemical resistance, right? The ability to block vapors, and what we call constructability, meaning like how easy is the barrier installed, or more importantly, the quality of that installation. I think it's really the combination of these two factors that often determine which barrier is selected on any given project. There's certainly a third criteria that's not shown, and that's of course cost, which is always an important factor. I will say Monoshield is priced competitively with other sheet vapor barriers in the market. But for today, I'm going to focus on constructability. Before I do that, a quick note on chemical resistance, because it's an incredibly important aspect of evaluating vapor barriers, and it's something regulators, design engineers, consultants often look at first. I'll note Monoshield, along with all other Land Science vapor barriers, go through rigorous testing to ensure they're compatible with site contaminants such as chlorinated solvents or BTEX. But constructability is kind of where I'll focus the rest of my time. We often say you can have the most chemically resistant vapor barrier in the world, but if it can't be installed in a timely manner or the seams can't be sealed properly, then really what good is it? When it comes to constructability, we look at kind of three areas, which I'll further expand on. But first, the speed of the vapor barrier installation. Second, the durability of the vapor barrier, meaning can it withstand construction activities like Mark just mentioned. And third, a certified installation, meaning is the vapor barrier installed by a contractor that has experience doing this work, or is it installed by a site contractor who is seeing this type of work for the first time? Before I get into detail on those three areas, it might be helpful to better understand the components that actually make up Monoshield. So on the left is a detail of Monoshield that shows the metallized film technology, GeoTextile fabric on the underside of the barrier, and a polyester reinforced grid on the top of the barrier. So the picture on the right, very similar to Mark's project, shows what Monoshield looks like when it's rolled out. The sheets are rolled out in the field. When it comes to constructability, though, the first area I'll discuss is installation speed. An old adage, I think, goes time is money. And installing a vapor barrier is really no different. What actually impacts the installation of a vapor barrier, though, for starters, we're looking at the production rate of installing that vapor barrier. This may seem like common sense, but if you look at the picture on the right side and the time it would take to seal the seams using those two different methods, the top shows the installation of Monoshield using a spray applied nitrile core. And the bottom shows a tape system with the seams being sealed by someone on their hands and knees. Now multiply this by 100,000, 300,000, 500,000 square feet, and the time to install vapor barriers can be substantially different. Next, how about weather? I'm based here in the Northeast, so that means I contend with winter weather, what honestly feels like probably half the year. Your project may be located where it rains on a daily basis. Contending with weather is something I think that is often overlooked. But having a vapor barrier system can greatly impact that installation time. I'd actually highly recommend reviewing some of the weather requirements when evaluating vapor barriers, because trying to tape seams together in the cold or the rain can actually be very difficult. I know two-sided tape and similar products work conceptually, but implementing it in the field, especially under poor weather conditions, can be an entirely different thing. Also, QA/QC procedures can impact the speed in which a vapor barrier is installed. So when I say QA/QC procedures, there are actually a number of things that fall underneath that umbrella. But one of the most important, as Mark mentioned a fair amount in his talk, was QA/QC, the procedure that we identify as smoke testing. So smoke testing is used to determine if the vapor barrier was installed properly by pumping smoke underneath the vapor barrier to see areas such as the seams, utility penetrations, perimeter terminations, that they were sealed properly. So getting a proper seal around those locations specifically in an efficient manner can greatly reduce the time needed in the field. Finally, consideration for what the project's construction activities will be. So how many concrete slab pours will there be? What equipment is needed? Will they be driving on the vapor barrier using a laser screed? I think Mark did a really good job touching on this, but the actual sequencing of these events can play a huge role in the speed of which the vapor barrier is installed. So here's a photo of a Monoshell installation that was took earlier this year, which I kind of hope captured some of the components of what I just discussed. This photo was taken on a January evening here in the Northeast, so weather certainly played a factor. Even in winter weather conditions, the applicator was installing at about 35,000 square feet per day and not really having any issues getting seals on those seams. This picture also kind of shows the level of construction activities that can take place on top of the barrier. Quick side note, in good conditions, our applicator's production rate can be even greater. Second consideration I'll mention is the durability of the vapor barrier. And I think highlighting what goes into durability of any vapor barrier is incredibly important. So to start, the thickness of the vapor barrier. I mean, a lot of times people equate thickness to chemical resistance, which in theory can be true. But the thickness of a barrier also matters when it comes to protection from construction-related activities. EPA in their 2008 document recommends a minimum thickness of 30 mil, which Monoshield does meet. So this is something to keep in mind, as anything less than 30 mil may not actually hold up to the construction activities. One reason Monoshield does hold up to heavy construction activities is the incorporation of the GeoTextile fabric on the underside of the barrier. So this added protection allows for a wider range of subgrade options, as larger stones can actually damage a thinner tape seamed vapor barrier. Also adding to the durability is how the seams are sealed together. So by spraying the seams with the nitrile core material, a seamless barrier is created, which actually increases the overall integrity of the system. And finally, as you can see in the foreground of this picture, Monoshield includes a polyester reinforced grid that increases the barrier's puncture and tear resistance. As an example of why sprayed seams and seam durability are so important, so here's a picture of Monoshield installation from late last year. On this project, about 100,000 square feet of Monoshield was installed one day prior to the scheduled concrete pour. At night, we had a pretty vicious storm come through and actually blew the barrier not only out of place, but the storm actually twisted up the vapor barrier and was very similar to like a corkscrew. Actually, this picture doesn't even do justice to how bad the storm was. So at first it was thought, well, that entire 100,000 square feet would need to be reinstalled, which would have cost everyone involved a lot of time and money to get new material, man hours to reinstall the barrier, delays to the concrete pour, and ultimately delays to the project. As it turns out, none of that ended up being true. So as you can see here, the vapor barrier was untwisted and pulled back into place. The spray applied seams held together across that entire 100,000 square foot area with only minor repairs being needed. Our applicator actually went back, recompleted smoke testing, so they met our specifications to ensure that it met all requirements of the project. So using a vapor barrier such as Monoshield here over, say, a taped vapor barrier system saved what would have been significant delays and additional costs to the project. The last topic I'll mention when it comes to construction considerations is using a product that requires a certified installation process, which includes certified installers, proper QA/QC procedures, which I've touched on, adequate inspection requirements, various warranty options. In our experience, having an applicator that has decades of experience installing vapor barriers is critically important to the success of a project. As I mentioned, as Mark mentioned, working on an active construction site, there's just too many variables that can really disrupt the installation of any vapor barrier. Therefore, Land Science has a network of certified installers that are experienced and trained to install all of Land Science's vapor barriers and can quickly troubleshoot any potential in-field issues. In addition, most of the applicators can provide their own workmanship warranty. I guess it comes down to this, and maybe these two pictures might reinforce what I'm going to say. You as the regulator or the design engineer, the property developer, or the owner have come to a decision that a vapor barrier is needed to protect future occupants of a building, needed for long-term liability of a project, whatever it may be. I'd also imagine significant time and money went into that decision process. So why risk the vapor barrier not being installed properly or not being installed properly because an inexperienced contractor attempted to install that vapor barrier? In our opinion, it makes a lot more sense to have an experienced contractor handling this work. And that's why we're so adamant about having a certified applicator network and so adamant that they're continuously trained and equipped to install any of Land Science's barriers. I could probably keep going, but I would imagine I'm out of time here. So I'll end with a few takeaways. Time is money. The infield installation can make or break a project. We've seen numerous projects run into significant delays because the vapor barrier couldn't keep up with the construction schedule. Consider all aspects of your construction process, rebar placement, other trades working around the barrier, the concrete pour. All of these things will happen on or near the vapor barrier, whether you like it or not. So you should have a barrier that holds up to some level of activity. And finally, a certified installation can go a long way in reducing long-term liability, something that I'm sure your clients would be happy to hear. So with that, I am finished. I appreciate everyone sticking around and we'll be happy to answer any questions.
All right. Thanks very much, Ryan. That concludes the formal section of our presentation. So at this point, we'd like to shift into the question and answer portion of the webcast. Before we do this, just a couple of quick reminders. First, you will receive a follow-up email with a brief survey. We really appreciate your feedback, so please take a minute to let us know how we did. Also, after the webinar, you will receive a link to the recording as soon as it is available. All right, so let's circle back to the questions. If we're unable to get to your question, we will follow up with you after the webinar. All right, so here's a question for Mark. And Mark, the question is, how did you achieve the production capacity for the install at this site?
Thanks, Dane. So the vapor installation contractor bid a very aggressive schedule. They actually were working 7 days a week, 12-hour days, and it was difficult for actually us to be able to staff that with inspectors. And we ended up having a team of inspectors that were rotating in and out because they never stopped, because they were always, there was never any downtime, so they always were working in one building or the other. And we were basically working with a shift split of like 4 days on and then 4 and 3. So someone would work for 4 days, someone would work for 3. But yeah, it was put down with 7 days a week, 12 hours a day.
All right, thanks, Mark. So here's another question. This question is for Ryan, and the question is, what is the cost per square foot for Monoshield?
So how did I know cost might be the first question? I'll say this with respect to cost. if you're familiar with costs of a typical 20 mil tape system, Monoshield will certainly be in line with those products. However, and as I mentioned kind of during my talk, the real savings with Monoshield will come with the installation time, because we're installing the barrier that much quicker.
Okay. All right. Thanks, Ryan. So here's another question for you, Mark. And the question is, where do you see most smoke tests fail?
Sure, that's a good question, and actually I think it dovetails a little bit on what Ryan just said. Is that one of the things I really liked about Monoshield was that, you know, there's one thing to talk about the time it takes to put the thing down, but there's another thing to say it's not really complete until it's past the smoke test, right? And the amount of time that it can take to fix a smoke test can be a lot if the system is not put down properly or doesn't have tight seams. And what I have found is, you know, colloquially, a lot of like inexperienced contractors seem to think that it's the penetrations that cause the most problems. But, you know, that might have been the case a long time ago, but I feel that most barrier systems, Monoshield in particular, have good penetration details that have been, you know, tested over time. And so generally speaking, I found that it's not really penetrations that I find. I mean, sometimes they leak, but honestly, they don't leak that much, and the contractors are usually pretty good about it in terms of sealing it. I find most of the problems for tape systems at the seams and in general at the walls, the wall terminations. And a lot of times what we actually recommend is not to have a piece of fabric that basically runs all the way up into the wall, turn up and seal to the wall. We actually basically cut off like a piece, or ask the contractor as part of our design to cut off like a piece and adhere that to the wall, come off the wall a certain amount, and then basically tie those two pieces together like an overlap. And that just reduces the amount of pulling or tearing forces that could be placed on it through the subsequent construction work. But I would say that's where I find most of the problems, is actually at the wall transitions.
Okay. All right. Thanks, Mark. So another question for you, and it's related a little bit to the last question that you just answered. This person says, you mentioned a secondary smoke test. So can you talk a little bit more about that and how you did those?
Yeah, sure. So, you know, a traditional smoke test is typically done after the barrier is put down. You cut a hole in the barrier, and then you basically do a 360-degree smoke test, often using kind of like a Halloween Party City smoke machine combined with like a pulsing leaf blower. So you're kind of like pulsing pressure and smoke, and you're lifting the barrier just a little bit with a cushion of air, and that smoke is kind of running and then finding all the little holes and showing you where they are. But what we were concerned, and the regulatory agency was concerned with our approach, because they really wanted to make sure that we didn't pass a smoke test, put a bunch of stone on top of it, and then basically bury the problem that we then tear up as part of the process. So the secondary smoke tests we were pumping smoke beneath the barrier, but we couldn't cut it because it was covered with stone. But we had all these test ports and pipes and vent stacks, so we could tie into those, and they were strategically located to facilitate the post-stone placement smoke test, as well as final O&M, which is a whole other topic that's not part of this talk. And so we were able to do that and use those kind of strategically. It was all built in as a cohesive system, and we were able to pump smoke. And like I said, there was one area that did fail, and we verified when we looked into it what the problem was. And so we felt pretty good about it.
Okay, thanks, Mark. Let's see. So here's another question regarding Monoshield. So this is a question for you, Ryan. It is, what types of sites is Monoshield recommended for?
Thanks. So I guess there's really two ways I can answer this question, whether that's building type or type of contamination. So first, for building type, as kind of outlined in the webinar today, Monoshield makes a lot of sense for projects with large building footprints, such as warehouses, big box retail, things like that. But we've installed Monoshield on various types of other buildings, so it really probably comes down to the specifics of the site. And then I guess with respect to contamination, again, Monoshield has been installed on projects with wide-ranging contaminants. So maybe rather than offering a blanket statement on compatible contaminants, I recommend maybe reaching out to one of us here at Land Science, and we can maybe review the specific contaminants at your site.
Okay, thanks, Ryan. So here's another question for Mark. And the question is, can you talk more about how you would do vertical terminations at a perimeter wall with Monoshield?
Sure. I would recommend this for Monoshield and really any system, and I briefly talked about this in my other answer. But I really think that, what I have noticed in my experience over time is that, you can seal a barrier, with a 90-degree turn up pretty well and have that fail because somebody steps on it, and either there's a void or there's pressure, or even when they lay the concrete, maybe they place the rebar with good care, but they, something happens and they just put too much force and it pulls it right off the wall and rips that seal. And then if you did a smoke test, after the fact, it would fail. So like I said, I really recommend basically if you look at the Monoshield detail, it calls for, you spray it against the wall, you turn it up and you stick it on there, and then you spray it over top of it. And I really like that, and I think it works really well. And again, I use tape systems sometimes, but it is a pain in the butt to pass a smoke test because that butyl tape has to be 100% flat. You stick it up against that two-sided tape, and then you got the tape on top, and all of it has to be perfect. And I have found that without using mechanical turn bars, often that's difficult to pass a smoke test. But for Monoshield, like I said, I would cut a separate piece of fabric. Probably it would go up the wall per the spec. It would come off the wall enough that you can tie into it as a seam, and not have that kind of direct stress right there, kind of pulling it from really far away. Because you don't want something that happens, 10 feet away from the side of the wall to somehow like put pressure on the wall itself. Obviously they're all connected, but there's some elasticity involved when you have the seams, and I just think that works better.
All right, thanks very much, Mark. That is going to be the end of our chat questions. If we did not get to your question, someone will make an effort to follow up with you. For more information about services from SME, you can visit sme-usa.com. If you would like to learn more about vapor intrusion solutions from Land Science, please visit landsciencetech.com. Thanks again to our presenters, Mark Quimby and Ryan Miller, and thanks to everyone who could join us. Have a great day.